In this video, we'll study the concept of braking in traction work. Braking is nothing but reducing the speed so that the vehicle can be brought to rest. In traction work, electrical braking and mechanical braking are employed for bringing the vehicle to rest. Mechanical braking is in which the braking force is applied by the rubbing action of brake blocks on the thread of the wheels. Electrical braking, it cannot be done with the mechanical brakes since vehicle cannot be held at stationary position by its use. The advantages of using electrical braking is that it reduces the wear on the mechanical brakes and it results in higher retardation, thereby bringing the vehicle to rest quickly and reducing the running time. When regenerative braking is employed, part of the energy is returned to the supply, thereby resulting in savings in the running cost. There are three methods employed for electrical braking. They are plugging, rheostatic braking, and regenerative braking. Plugging. In plugging, the connection of the motor armature is reversed so that the motor tends to rotate in the reverse direction, thus providing the necessary braking effect. But the supply must be cut off when the motor comes to rest, else the motor will start rotating in the reverse direction. Plugging can be employed for DC, induction and synchronous machines. The plugging for DC series motor is as shown in the figure. The armature connection is reversed with respect to the field so that the current in the armature reverses. During the normal running, the back EMF E, it is opposite to the direction of armature current, but during braking, back EMF E and the armature current are in the same direction. At the instant of armature connection reversal, a voltage equal to V plus E is applied across the motor armature circuit, where V is the supply voltage and E is the back EMF, and E is proportional to V. Therefore, a voltage of 2V is applied across the motor armature circuit. This results in a high rush of current in the armature circuit. To limit this current, a starting resistance is reinserted in the armature circuit. During braking, in addition to the kinetic energy of the motor, which is dissipated in the resistance, some energy is drawn from the supply, which will be dissipated in the resistance. Therefore, it will be a waste of energy. Next method of electrical braking is rheostatic braking. When two or more series motors are used for traction work, the motors will be connected in parallel across a resistance. The kinetic energy will be utilized in driving the motors as generators, which will be dissipated in the form of heat in the rheostats connected. The two machines in parallel will equal to two series generators in parallel, and to self-excite it, an equalizer connection will be used as shown in the figure. If the equalizer connection is not used, then the machine which will build up first will send a current through the other in the reverse direction, resulting in the second machine exciting with the reversed voltage. Therefore, the two machines will be short-circuited on themselves and it might burn out due to large current value. The equalizer will prevent such a condition. Another way of rheostatic braking is to cross-connect the fields of the two motors as shown in the figure. Suppose the voltage of motor 1 is greater than that of motor 2. It will send larger current through the field of motor 2, causing it to excite to a higher voltage. But its own excitation will be kept down because of the induced EMF of motor 2, which is less. Thus, automatic compensation is provided and the two machines will operate satisfactorily. Next is regenerative braking. In that we have mechanical regenerative braking. So when the train is accelerated up to a certain speed, it acquires kinetic energy corresponding to that speed. During the coasting period, part of this kinetic energy is utilized in overcoming the frictional resistance offered, and some part is utilized in the propulsion of the train. The kinetic energy which is utilized in the propulsion of the train does the useful work. Therefore, the coasting is referred as mechanical regenerative braking, since the speed gradually decreases due to the utilization of kinetic energy stored in the train at the end of accelerating period. A system of track grading is employed in the case of underground railways, where the kinetic energy is used in doing the useful work against gravity. There are two types of graded tracks as shown in the figure. When the train is at station A, it possesses certain potential energy which is utilized in its descending down the gradient till it reaches the level tracks. But graded track construction, it is only possible in case of underground railways and it is not practicable for surface railways. Regenerative braking on a level track. When regenerative braking is employed on a level track, the amount of energy returned to the line depends on the initial and final speed during regenerative braking, the efficiency of the system, and train resistance. If regenerative braking starts at a speed of V1 km per hour and ceases at a speed of V2 km per hour, then the kinetic energy stored in the train at a speed of V1 km per hour is equal to half into 1000 WE into V1 into 1000 by 3600 square into 1 by 3600 watt hours. Since we have kinetic energy equal to half mv square, where m is the mass and v is the speed, which is equal to 0.01072 V1 square WE watt hour. That is equal to 0.01072 V1 square WE by W watt hour per ton. Similarly, kinetic energy at speed V2 km per hour is equal to 0.01072 V2 square into WE by W watt hour per ton. Therefore, energy available is equal to 0.01072 WE by W into V1 square minus V2 square watt hour per ton. If D is the distance covered in kilometer during regenerative braking, we have D equal to half V1 plus V2 into T2 by 3600, and T2, the time duration for coasting, is V1 minus V2 by beta C. Therefore, D is equal to half V1 plus V2 into V1 minus V2 by beta C into 3600. That is equal to V1 square minus V2 square by 2 beta C into 3600. The energy utilized in the train resistance is 0.0278 Rd, where R is the specific resistance in newtons per ton and D is the distance covered during regenerative braking. Therefore, energy utilized equal to 0.0278 Rd in watt hours per ton. That is equal to 0.0278 R into V1 square minus V2 square by 2 beta C into 3600. That is equal to 0.0139 V1 square minus V2 square R by 3600 beta C in watt hour per ton. Therefore, energy returned to the line is equal to neta into energy available minus energy utilized, that is neta into 0.01072 We by W into V1 square minus V2 square minus 0.0139 into V1 square minus V2 square R by 3600 beta C in watt hours per ton, where neta is the efficiency of the system. Next topic is regenerative braking with DC motors. The terminal voltage of the DC motor, it should be greater than the supply voltage for the regeneration to take place in the DC motor. Also, this voltage should be held constant at this value irrespective of the variation in speed or the braking torque. So the DC series motor needs some modification so that it can be used for regenerative braking. During regeneration, the current through the armature reverses, and since the excitation of the field has to be maintained, the field connection should be reversed. So as to avoid the short circuit condition. So if the field connections are not reversed, the regenerated current in the field will reverse the field, which will reverse the back EMF of the motor, and hence the supply voltage V and the back EMF E will aid each other, resulting in short circuit condition. One method of regenerative braking for series motors is the French method. As shown in the figure, a series motor with its main series field winding is connected across main series field auxiliary windings. So during regenerative braking, the auxiliary field windings will be placed in series with each other, and it will be placed across the armature and the main series field winding. So the machine will act as a compound generator, and if there is a slight change in the line voltage, the shunt excitation, which is sensitive to such changes, will result in the EMF of the generator to increase or decrease, thus providing the necessary balance. That is, if the line voltage tends to increase beyond the EMF of the generator, the increased voltage across the shunt circuit will result in large exciting current through it, causing the EMF of the generator to rise. And the reverse happens when the line voltage tends to fall. So this arrangement is called self-compensating. In locomotives where 4 or 6 series motors are used, then there is no need to use the auxiliary windings. During normal working, all the motors will be in series with their respective field windings as shown in the figure, but during regeneration, the motor armatures will be in parallel with the field windings of all other motors except one. An alternative method of regenerative braking is using an exciter to control the excitation of the field winding during regeneration. The exciter is either axle driven or driven by motor operated from auxiliary supply. As shown in the figure, the exciter E, it has separately excited winding whose excitation is controlled by the driver, and it has a series winding which is connected in the main motor circuit in such a way that it opposes the separately excited winding during regeneration. The series winding is F2 and the separately excited winding is F1. So F1 and F2, they are arranged to oppose each other during regeneration. If the line voltage decreases, it will increase the regenerated current through the motor armatures, and the excitation of F2 will therefore increase. And since F1 and F2 are opposing each other, the excitation of F1 will decrease, which will result in decrease of EMF of the exciter E. So when the EMF of the exciter falls, the current in the field of motor 1 and 2 decreases, which will result in EMF of motor 1 and 2 to decrease. Hence, there is compensation provided for the decrease in the line voltage. In the figure 2, we have the exciter armature connected in the circuit of the field windings and the stabilizing resistance. So the current in the stabilizing resistance is equal to the regenerated current plus the exciter current. If the line voltage falls, then the regenerated current increases. This will cause greater voltage drop across the stabilizing resistance. So the balance of voltage available in the exciter armature circuit is reduced, which will result in reduction in the exciting current for the fields of motor 1 and 2. This will decrease the induced EMF of the generators, thus providing the compensation. The function of the stabilizing resistance is to prevent the current surge when the vehicle crosses one section of the supply to another and to compensate for the variation in the line voltage.